Hey guys, tonight we begin with something a little darker. A biological reality so fundamental, yet so terrifying, that your body has built an entire emergency system around it. We're diving into what happens when the one thing you can't live without, oxygen, suddenly disappears. Forget dramatic movie deaths. The truth is far more complex, far more biological, and honestly, far more fascinating than Hollywood could ever show you. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Maybe share how many breaths you think you take in a single day. Most people get it wrong by thousands. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Congratulations! For the next hour or so, we're going to explore something your body does automatically, approximately 20,000 times every single day, without you ever thinking about it. Until, of course, it can't. Right now, as you're listening to this, your diaphragm is contracting, your ribcage is expanding, air is flowing into your lungs through passages the width of a pencil lead. And at the end of those passages, in tiny sacs called alveoli, oxygen is crossing into your bloodstream through membranes thinner than tissue paper. You didn't ask for any of this to happen. You didn't consciously command your lungs to inflate or your heart to pump oxygenated blood to your brain. It just happens. Breath after breath after breath. Roughly 12 to 20 times every minute. Over 8 million times a year. And if you live to be 80 years old, you'll have taken somewhere around 600 million breaths in your lifetime. But what happens when that rhythm stops? Not because you're holding your breath during a swimming pool dare, but because oxygen itself vanishes. No air, no rescue, just your body, your biology, and a clock that starts counting down the moment your last breath escapes. What happens in the first 15 seconds? The first minute? The critical 3 to 4 minute window when your brain begins to die? And why does suffocation feel the way it does? The burning, the panic, the desperate need to breathe, it's not actually caused by lack of oxygen. It's caused by something else entirely. Tonight, we're going to walk through it, slowly, carefully, and with the kind of detail that helps you understand just how remarkable your respiratory system really is. Because the biology of suffocation isn't just about death. It's about the extraordinary lengths your body will go to keep you alive. Every system, every cell, every molecule working in concert to protect the one organ that matters most, your brain. And when that protection fails, the cascade that follows is as precise as it is devastating. So settle in, get comfortable, because we're about to explore what your body does when it can't do the one thing it was designed to do. Breathe. Let's start with the breath you're taking right now, not the one you just took, the one happening as you hear these words. Feel it, the gentle rise of your chest, the cool air moving through your nostrils, the quiet expansion of your lungs. This single breath, this ordinary, unremarkable inhale, is one of the most sophisticated biological processes your body performs. And you didn't even have to think about it. Here's what just happened. Air entered your body at roughly 15 miles per hour, though you'd never know it. It rushed past the tiny hairs in your nose, called cilia, which filtered out dust, pollen, and microscopic debris you don't even want to think about. The air then traveled down your trachea, a tube about 4 inches long and reinforced with rings of cartilage to keep it from collapsing. Think of it as biological scaffolding, always open, always ready. At the base of your trachea, the airway splits. Left lung, right lung. Two bronchi branching off like roads diverging in a forest. But the branching doesn't stop there. Each bronchus divides again and again and again, 23 times in total, each division creating smaller and smaller passages. By the end, you're left with bronchioles so narrow they're barely visible to the naked eye, tubes thinner than a strand of hair, delivering air to the deepest reaches of your lungs. And at the very end of this intricate network are the alveoli. If you've never heard of them, don't worry, most people haven't. But you have about 300 million of these tiny, grape-like sacs clustered at the terminals of your airways. 300 million. If you could spread them all out flat, they'd cover an area roughly the size of a tennis court. All of that surface area, folded and packed inside your chest, exists for one purpose: gas exchange. This is where the magic happens. Each alveolus is wrapped in a net of capillaries, blood vessels so thin that red blood cells have to squeeze through them single file. The wall separating the air in your alveoli from the blood in your capillaries is almost impossibly delicate, half a micron thick. That's about 1/200th the width of a human hair, thin enough that oxygen molecules can pass through with ease. So here's the exchange. Oxygen from the air you just inhaled diffuses across that microscopic membrane and binds to hemoglobin inside your red blood cells. Hemoglobin is a protein, shaped like a four-leaf clover, and each molecule can carry up to 4 oxygen atoms. When oxygen latches on, hemoglobin changes color. Dark red becomes bright red, deoxygenated blood turns into oxygenated blood, and just like that, your lungs have done their job. But it's a two-way street. While oxygen is moving into your blood, carbon dioxide is moving out. Carbon dioxide is the waste product of cellular respiration, the metabolic process happening in every cell of your body right now. Your cells burn glucose and oxygen to create energy, and carbon dioxide is what's left over. It travels through your bloodstream back to your lungs, diffuses into the alveoli, and gets exhaled out into the world. Gone. This entire process, from inhale to oxygen binding to carbon dioxide release to exhale, takes about 3 to 5 seconds. You do it 12 to 20 times per minute without ever consciously deciding to. Even right now, as you listen, your brainstem is sending signals to your diaphragm. The dome-shaped muscle sitting just below your lungs, contract, relax, contract, relax. It's automatic, involuntary, a rhythm your body has been maintaining since the moment you were born. And here's the part that should terrify you. This system, elegant as it is also fragile. Your brain can survive without food for weeks. It can survive without water for days, but without oxygen, minutes, just minutes. Because every cell in your body, but especially the cells in your brain, depends on a constant supply of oxygen to function. There's no storage, no backup tank, no reserves. You live breath to breath, moment to moment, entirely dependent on this continuous cycle of air in, air out. Let's put it in perspective. Your brain makes up only about 2% of your body weight, but it consumes roughly 20% of the oxygen you breathe. 20%. That's because neurons, the cells in your brain, are incredibly energy hungry. They're firing constantly, sending electrical signals, maintaining connections, processing information. All of that requires fuel, and fuel, in biological terms, means glucose and oxygen combining to produce ATP, the molecule that powers every cellular process in your body. Without oxygen, ATP production grinds to a halt, And when that happens, everything else follows. Neurons stop firing. Muscles stop contracting. Your heart, which is just a specialized muscle, starts to falter. Consciousness fades. And if oxygen doesn't return soon, the damage becomes permanent. But here's what makes suffocation so uniquely cruel. The act of breathing feels effortless because your body has designed it that way. Your diaphragm does most of the work. Your intercostal muscles, the ones between your ribs, assist. Together, they create negative pressure inside your chest cavity, and air rushes in to fill the void. It's passive, automatic. You never have to think about the mechanics because your medulla oblongata, a small region at the base of your brain, handles all of it for you. Until something goes wrong, until the air stops coming, until your body realizes that the oxygen it's been counting on, the oxygen it needs more than anything else, is suddenly terrifyingly absent. And that's when everything we've just talked about, this beautiful, efficient, life-sustaining system, becomes a countdown, a race against time, a biological crisis unfolding in real time, 1 second at a time. So the next time you take a breath, maybe appreciate it a little more, because that simple act, that rise and fall of your chest, is the only thing standing between you and the suffocation we're about to explore. So, oxygen makes it into your bloodstream. Your hemoglobin grabs it, turns bright red, and off it goes, carried through your arteries to every corner of your body. But here's the question most people never ask. What happens next? What does oxygen actually do once it arrives at your cells? Because breathing isn't the end of the story. It's just the delivery system. The real work, the reason you need oxygen at all, happens inside your cells. And it's happening right now, trillions of times per second, in a process so fundamental that without it, you wouldn't last more than a few minutes. Welcome to cellular respiration. Not the kind of respiration where your lungs move air in and out. This is deeper. This is the microscopic furnace burning inside every single cell in your body, and the star of the show, a tiny organelle called the mitochondrion. You've probably heard it called the powerhouse of the cell, a phrase hammered into students in biology class and promptly forgotten. But it's true. Mitochondria are power plants, and oxygen is the fuel they desperately, constantly need. Let's zoom in. Imagine a single cell in your body. Could be a neuron in your brain, could be a muscle cell in your leg, doesn't matter. Inside that cell, floating in the cytoplasm, are hundreds, sometimes thousands of mitochondria. They look like tiny beans under a microscope, each one wrapped in a double membrane, folded and convoluted to maximize surface area. And inside those folds, a chemical reaction is taking place that makes everything else possible. Here's how it works. Your cells take in glucose, a simple sugar that comes from the food you eat. Glucose is broken down in a series of steps, first in the cytoplasm through a process called glycolysis, then shuttled into the mitochondria for the main event. This is where oxygen comes in. Inside the mitochondria, glucose is fully oxidized, burned, essentially. The carbon atoms in glucose combine with oxygen to produce carbon dioxide, water, and most importantly, energy. But not just any energy. The energy is captured in the form of a molecule called adenosine triphosphate, ATP. If you want to understand why suffocation kills, you need to understand ATP. It's the universal energy currency of life. Every time a muscle contracts, every time a neuron fires, every time your heart beats, ATP is being consumed. Imagine it as a tiny, rechargeable battery. When a cell needs energy, it breaks off one of the phosphate groups from ATP, releasing a burst of power. What's left is ADP, adenosine diphosphate, which gets recycled back into ATP as long as oxygen keeps flowing. One molecule of glucose, fully metabolized with oxygen, produces around 30 to 32 molecules of ATP. That's a huge return. But here's the catch. Without oxygen, that same molecule of glucose can only produce 2 molecules of ATP through glycolysis alone. 2. You go from 32 down to 2. That's a 94% loss in energy production. Your cells can survive on glycolysis for a little while, but not long. Not nearly long enough. This is why your brain is so vulnerable. Neurons are energy gluttons. A single neuron can consume around 4.7 billion ATP molecules per second. Yes, billion, with a B. And your brain has roughly 86 billion neurons. Do the math. That's an incomprehensible amount of energy demand. Your brain doesn't store energy. It doesn't have reserves. It lives moment to moment, entirely dependent on a constant supply of glucose and oxygen delivered by your blood. So what happens when oxygen stops arriving? At first, nothing dramatic. Your cells have a tiny reserve of ATP already on hand, enough to keep things running for a few seconds. But once that's depleted, they switch to anaerobic respiration, metabolism without oxygen. Glycolysis kicks into overdrive, breaking down glucose as fast as it can to squeeze out those 2 measly ATP molecules. But there's a problem. Anaerobic respiration produces lactic acid as a byproduct. You've felt this before. It's the burn in your muscles when you sprint too hard, when your muscles can't get oxygen fast enough, and lactic acid starts accumulating. That burn is your cells screaming for oxygen. In your brain, lactic acid buildup is even more dangerous. Neurons are exquisitely sensitive to changes in pH, the acidity of their environment. As lactic acid accumulates, the pH drops, the environment becomes more acidic, and neurons don't like that. They start misfiring. Electrical signals become erratic. Neurotransmitters, the chemical messengers that allow brain cells to communicate, stop being released properly. Consciousness, which depends on coordinated electrical activity across billions of neurons, begins to flicker. But the real crisis happens at the mitochondrial level. Remember, mitochondria need oxygen to run the electron transport chain, the final step of cellular respiration where most ATP is produced. Electrons are passed along a series of protein complexes embedded in the inner mitochondrial membrane, and oxygen is the final electron acceptor. It's the last stop. Without oxygen, the entire chain backs up. Electrons have nowhere to go. The proteins involved start to malfunction. And ATP production doesn't just slow down, it stops. When that happens, the sodium-potassium pump fails. This pump is one of the most important proteins in your cell membranes. It uses ATP to move sodium ions out of the cell and potassium ions in, maintaining the electrical charge that allows neurons to fire. Without ATP, the pump stops working. Sodium floods into the cell, potassium leaks out. The cell swells with water, a process called cytotoxic edema. The membrane destabilizes, and if this goes on long enough, the cell ruptures. It dies. This is happening in every oxygen-starved cell in your body, but it's most catastrophic in your brain. Brain cells don't regenerate the way other cells do. Once a neuron dies, it's gone. No replacement, no backup, just permanent loss. And the areas of your brain that control consciousness, memory, movement, and thought are all made up of these fragile, irreplaceable cells. So when we talk about suffocation, we're not just talking about the absence of air, we're talking about the collapse of cellular metabolism, the shutdown of mitochondria, the depletion of ATP, the failure of every energy-dependent process in your body. Your cells are molecular machines, and oxygen is the fuel that keeps those machines running. Take it away, and the machinery grinds to a halt. First, gradually, then suddenly, then catastrophically. And here's the terrifying part. You don't feel any of this. You don't feel your mitochondria failing. You don't feel your ATP reserves draining. You don't feel your neurons swelling and dying. By the time you realize something is wrong, the damage has already begun. Because suffocation doesn't announce itself with pain. It announces itself with confusion, with dizziness, with a creeping sense that something, somewhere deep inside, is going terribly, irreversibly wrong. So the next time you think about oxygen, don't just think about breathing. Think about the trillions of mitochondria inside you, working every second of every day, burning fuel to keep you alive. Because when they stop, everything else stops too. Let's say it happens. Right now, the oxygen stops. Maybe you're underwater and something goes wrong. Maybe there's a gas leak and the air in the room is suddenly unbreathable. Maybe your airway is blocked. It doesn't matter how. What matters is this. One moment you're breathing normally, and the next moment you're not. The clock starts, and in the first 15 seconds, something very strange happens. Almost nothing. That might sound wrong. You'd think your body would immediately panic, that alarms would go off, that you'd feel the danger instantly. But you don't. Not yet, because your body has a buffer, a reserve. Not a large one, but enough to buy you a few precious seconds before the crisis truly begins. And that buffer is already circulating through your bloodstream right now, bound to hemoglobin, waiting to be delivered. Here's what most people don't realize. At any given moment, your blood is carrying enough oxygen to keep your brain and vital organs functioning for about 15 to 20 seconds without a single new breath. It's not a storage system, exactly. It's more like the oxygen that's already in transit. Think of it like a delivery truck that's already left the warehouse. Even if the warehouse suddenly shuts down, the truck is still on the road, still carrying its cargo, still making deliveries. Your hemoglobin molecules are those trucks. Each red blood cell is packed with roughly 270 million hemoglobin molecules. And each hemoglobin molecule is carrying up to 4 oxygen atoms. Multiply that across the 25 trillion red blood cells in your body, and you have an enormous amount of oxygen already loaded and moving through your circulatory system. That oxygen is being delivered to cells, released and consumed, all while your heart continues pumping blood exactly as it always has. So in the first few seconds after oxygen stops entering your lungs, nothing changes. Your brain doesn't know yet. Your cells don't know yet. They're still receiving oxygen from the blood. ATP is still being produced in your mitochondria. Neurons are still firing. Your heart is still beating. Consciousness remains perfectly intact. You might not even realize anything is wrong. If you're holding your breath voluntarily, you feel fine, calm, even. The discomfort hasn't started yet. But here's where it gets interesting. Your body does have sensors, chemoreceptors. They're located in 2 main places: the carotid bodies, small clusters of cells in your neck near the carotid arteries, and the aortic bodies, located in the arch of your aorta near your heart. These chemoreceptors are constantly monitoring your blood. They're checking oxygen levels, yes, but more importantly, they're checking carbon dioxide levels and blood pH. And here's the strange part. These sensors are far more sensitive to carbon dioxide than they are to oxygen. Your body doesn't actually have a great early warning system for low oxygen. What it does have is an extremely sensitive alarm for high carbon dioxide. Because in normal circumstances, when you stop breathing, carbon dioxide builds up quickly. It's the waste product of cellular respiration, remember. Your cells are constantly producing it, and if you're not exhaling, it accumulates in your bloodstream, making your blood more acidic. This is why holding your breath feels the way it does. That burning sensation, that desperate urge to breathe, it's not because you're running out of oxygen, not initially anyway. It's because carbon dioxide is building up and your chemoreceptors are screaming at your brain to do something about it. They're sending signals to the respiratory centers in your brainstem saying, exhale, inhale, get rid of this carbon dioxide, bring in fresh air, do it now. But in true suffocation, where oxygen is absent but you're still able to exhale, the signals get confused. If you're in an environment filled with an inert gas like nitrogen or helium, gases that don't trigger your carbon dioxide sensors, you can lose consciousness without ever feeling the urge to breathe. This is how people die in confined spaces, in industrial accidents, in poorly ventilated areas. They walk into a room, take a breath of air that contains no oxygen, and within seconds, they're unconscious. No warning, no panic. Just a quiet, sudden loss of awareness. It's one of the most insidious ways suffocation can happen. Because your body's primary alarm system, the one that detects rising carbon dioxide, never goes off. You're breathing, you're exhaling carbon dioxide just fine, but you're not getting any oxygen. And by the time your body realizes something is wrong, by the time your oxygen levels drop low enough to trigger a response, it's often too late. So in these first 15 seconds, your body is in a strange limbo. The oxygen reserve in your blood is being consumed, your cells are still functioning, but the supply isn't being replenished. It's like draining a bathtub with the faucet turned off. For a while, there's still water, but the level is dropping, and once it's gone, it's gone. Your brain, consuming roughly 20% of your body's oxygen, despite being only 2% of your body weight, is burning through its share fastest. Neurons are energy hogs. They don't slow down, they don't go into hibernation mode. They keep firing, keep communicating, keep consuming ATP, which means they keep consuming oxygen. Every second that passes without a fresh supply is a second closer to depletion. Meanwhile, your heart is still beating, 60 to 100 times per minute, depending on your resting heart rate. It's pumping blood through your lungs, but the blood isn't picking up any new oxygen, it's just circulating what's already there. The bright red oxygenated blood leaving your heart starts to darken as cells extract the oxygen they need. The gap between oxygen delivery and oxygen demand is widening, and your body, for now, is blissfully unaware. Here's the thing. 15 seconds doesn't sound like much, but in terms of biological processes, it's an eternity. Your heart beats roughly 15 to 25 times. Your brain processes thousands of signals. Your cells produce and consume millions of ATP molecules. Life at the cellular level moves fast. And when the fuel runs out, the collapse happens just as quickly. There's a strange mercy in this brief window. If you're drowning, if you're choking, If you're suffocating, these first 15 seconds are the calmest you'll experience. You might feel confusion. You might feel the first flutter of concern, but the panic hasn't hit yet. The physiological storm hasn't begun. Your consciousness is still clear. Your thoughts are still coherent. You're still you. But the clock is ticking. The oxygen reserve in your bloodstream is finite. And once it's depleted, once your cells start running on empty, everything changes. The calm shatters. The body's emergency systems activate. And the real crisis, the one your body has been quietly preparing for, finally begins. So enjoy these 15 seconds, because they're the last moments of normal your body will experience until oxygen returns, or doesn't. 30 seconds have passed, maybe 45. Your oxygen reserve, the hemoglobin molecules still carrying their cargo through your bloodstream, is running low. The delivery trucks are almost empty. And now, for the first time, your brain begins to notice. Not consciously, not with words or thoughts, but deep in the primitive centers of your brainstem, alarms are starting to sound. Oxygen saturation is dropping, and your brain, the most oxygen-hungry organ in your body, is about to make that everyone else's problem. Here's what's happening. Under normal conditions, your blood oxygen saturation, the percentage of hemoglobin molecules carrying oxygen, sits comfortably between 95 and 100%. That's the baseline. That's what your body expects. But now, without new oxygen coming in, that number is falling. 90%, 85%, 80%. And your brain is exquisitely sensitive to this decline. The first areas to feel it are the ones that demand the most energy. The cerebral cortex, the wrinkled outer layer of your brain responsible for conscious thought, decision-making, and sensory processing, is one of the biggest energy consumers. Neurons in the cortex fire constantly, maintaining the complex network of activity that makes you aware, alert, and able to think. But neurons don't have backup generators. They live breath to breath, ATP molecule to ATP molecule. And when ATP production slows, they slow too. You start to feel it as a subtle shift, maybe a slight dizziness, a sense that the world is a little less sharp, a little less clear. Your thoughts might slow down, just a fraction. You might find it harder to focus, harder to process what's happening. This isn't dramatic yet. It's not a blackout. It's more like your brain is running on a dimming battery. The lights are still on, but they're flickering. Is less than #0, 7 hash is greater than. At the same time, your chemoreceptors, those sensors in your neck and chest that monitor blood chemistry, are screaming now. They've detected the drop in oxygen. They've also detected the rise in carbon dioxide, assuming you're holding your breath or unable to exhale properly. And they're sending urgent signals to the respiratory centers in your medulla oblongata. Breathe. Breathe now. Override everything else and breathe. But you can't, or you won't, or the air isn't there. So your body moves to plan B. It's called the hypoxic drive. Your brainstem starts sending more aggressive signals to your diaphragm and intercostal muscles. Contract harder, move more air, do whatever it takes. If you're conscious, you'll feel this as an overwhelming urge to breathe. It's not a suggestion. It's a primal, desperate command. Your body is trying to force you to inhale, whether you want to or not. Now let's talk about what's happening in your blood vessels. Your body has a hierarchy, a triage system, and at the top of that list is your brain. When oxygen levels drop, your cardiovascular system makes a choice. It's going to protect the brain at all costs, even if it means sacrificing everything else. Blood vessels in your extremities, your arms, your legs, your skin start to constrict. Vasoconstriction, it's called. The goal is to redirect blood flow away from the periphery and toward the core, toward your heart, your lungs, and most importantly, your brain. This is why people who are drowning or suffocating often have pale, cold skin. Their body has made a calculated decision. Fingers and toes don't matter right now. The brain does. So blood is shunted centrally, pooling in the vessels that supply your most vital organs. It's a desperate move, a last-ditch effort to keep the command center online for as long as possible. Meanwhile, your heart rate is changing. In some cases, it speeds up, trying to circulate the remaining oxygenated blood faster to squeeze every last bit of utility out of what's left. But in other cases, especially in cold water drowning or sudden airway obstruction, something strange happens. Your heart rate slows dramatically. This is called the mammalian dive reflex, an evolutionary remnant from our aquatic ancestors. When your face is submerged in cold water, sensors in your skin send signals to your brainstem, triggering bradycardia, a slowing of the heart. The idea, biologically speaking, is to conserve oxygen, slow the heart, reduce metabolic demand, stretch the oxygen supply as long as possible. It's a reflex you share with seals, dolphins, and whales, animals that dive deep and hold their breath for minutes at a time. In them, it's a survival adaptation. In you, it might buy an extra 30 seconds, maybe a minute. But it's not enough, because unlike a seal, you're not designed for this. Your brain can't tolerate prolonged hypoxia, and every second without oxygen pushes you closer to the edge. At around the 1-minute mark, your vision starts to change. Tunnel vision, it's called. The world narrows. Your peripheral vision dims, darkens, and eventually disappears. You're looking through a shrinking porthole. This happens because the cells in your retina, the light-sensitive tissue at the back of your eye, are starving for oxygen. The rods and cones, the photoreceptor cells that allow you to see, are some of the most metabolically active cells in your body. When oxygen drops, they stop working, and your visual field collapses inward. Your hearing might start to fade too. Sounds become muffled, distant, like you're underwater even if you're not. The cochlea, the spiral structure in your inner ear that translates sound waves into electrical signals, is also oxygen dependent. The hair cells inside it need a constant supply of ATP to function, and as ATP runs out, those cells stop responding. The world becomes quieter, dimmer, smaller. This is when panic usually sets in. If you're conscious, if you're aware of what's happening, your body floods with adrenaline. Your amygdala, the fear center of your brain, activates. Heart pounding, muscles tensing, thoughts racing. Every instinct you have is telling you to fight, to escape, to fix this. But if you can't breathe, if there's no air, panic doesn't help. It just burns through your remaining oxygen faster. Some people, trained divers, free divers, people who've practiced breath holding, can suppress this panic response. They've conditioned their minds to stay calm, even as their body screams for air. But for most people, this is the worst part. The terror, the helplessness. The knowledge that something is very, very wrong and there's nothing you can do about it. And your brain, still trying to maintain consciousness, is starting to lose the battle. Neurons are misfiring. Electrical signals are becoming erratic. The organized patterns of activity that create coherent thought are breaking down. You might feel confused, disoriented, time might stretch or compress. Memories might surface randomly, vividly, like your mind is rifling through files, trying to find something, anything that will help. This is the transition point, the moment when your body shifts from managing a crisis to losing control of one. The oxygen is nearly gone. The reserves are depleted, and in the next 30 to 60 seconds, consciousness itself will begin to slip away, not peacefully, not gently, but inevitably as your brain, deprived of the one thing it cannot live without, starts to shut down.
1 minute has passed, maybe 90 seconds. You're still conscious, but barely. Your brain is running on fumes.
The organized electrical patterns that create thought, awareness, and perception are starting to fracture. And now your body enters what might be the most agonizing phase of suffocation, the struggle, not the physical thrashing, though that might happen too, but the internal biological struggle as your respiratory system tries everything it can to force you to breathe. Here's where things get visceral. If you've ever held your breath as long as you could, maybe underwater in a pool or during some misguided challenge with friends, you've felt a version of this, that burning sensation in your chest, the overwhelming, almost painful urge to inhale. But that discomfort you felt, that was just the beginning. That was your body being polite. In true suffocation, when your oxygen levels plummet and carbon dioxide floods your system, polite goes out the window. The burning you feel, that desperate clawing need for air, it's not actually caused by a lack of oxygen, not directly. It's caused by carbon dioxide buildup. Remember, every cell in your body is still producing carbon dioxide as a waste product of metabolism. Your heart is still beating, your brain is still firing, your muscles are still working, and all of that activity generates carbon dioxide which dissolves in your blood to form carbonic acid. Your blood pH is dropping. It's becoming more acidic, and your chemoreceptors absolutely hate that. These sensors, located in your carotid arteries and your brainstem, are incredibly sensitive to changes in blood pH. Even a tiny shift, a drop of just 0.05 pH units, is enough to trigger a massive response. Signals flood into your medulla oblongata, the part of your brainstem that controls breathing. And the medulla responds by doing the only thing it knows how to do. It commands you to breathe, harder, faster, now. But you can't. So the signals intensify. Your diaphragm starts contracting involuntarily. These aren't the smooth, gentle contractions of normal breathing. These are violent, spasmodic jerks. If you're underwater, your body might try to inhale anyway, even though you know, consciously, that there's no air. This is called an involuntary inspiratory gasp, and if it happens underwater, you drown. Water rushes into your lungs, and the situation goes from critical to catastrophic. If you're not underwater, if your airway is simply blocked or the air around you is unbreathable, your body might trigger something called laryngospasm. This is a protective reflex. The muscles around your vocal cords suddenly clamp shut, sealing your airway completely. The goal is to prevent anything foreign, water, toxic gas, vomit, from entering your lungs. It's a last line of defense. But it also means you can't breathe at all, even if you wanted to. Your throat locks up, and the panic intensifies. At this point, your oxygen saturation has dropped dangerously low. 70%, 60%, maybe lower. Normal is 95 to 100. Anything below 90 is considered hypoxemia, low blood oxygen. Below 80 is severe. Below 70, you're in life-threatening territory. And your brain, which has been struggling to maintain function, is starting to lose the fight. The first thing to go is fine motor control. Your hands might tremble, your fingers might twitch. If you're trying to swim, trying to reach the surface, trying to remove whatever is blocking your airway, your movements become uncoordinated, clumsy, sluggish. This happens because the motor cortex, the part of your brain that controls voluntary movement, is exquisitely sensitive to oxygen deprivation. Neurons. They are firing erratically now, sending garbled signals to your muscles. Your vision, already narrowed by tunnel vision, might start to fade completely. Grey out, it's called. The world becomes a washed-out blur. Colours disappear. Shapes lose definition. This is your visual cortex shutting down, one layer at a time. The neurons responsible for processing visual information simply don't have enough energy to keep working. ATP levels in those cells have dropped too low. And without ATP, the sodium-potassium pumps fail. The cells depolarize, they stop firing. Consciousness, that fragile, flickering awareness of self and surroundings, is starting to slip. You might still be technically awake, but your thoughts are no longer coherent. Time becomes strange. Seconds might feel like minutes. Or everything might blur into a single, endless moment. Your sense of identity, of who you are and where you are, begins to dissolve. This is your prefrontal cortex failing, the part of your brain responsible for executive function, self-awareness, and rational thought. Some people report strange sensations during this phase, a feeling of floating, a sense of detachment from their body, visual or auditory hallucinations, memories surfacing with startling clarity, often from childhood. These aren't supernatural experiences. They're the result of a dying brain, misfiring, pulling random signals from deep storage, trying to make sense of a situation that has no sense left in it. Meanwhile, your body is making desperate adjustments. Your heart, still beating, is now racing. Tachycardia. It's trying to circulate what little oxygenated blood remains as quickly as possible. But the blood leaving your heart is dark now, deoxygenated. Hemoglobin molecules that have released their oxygen and picked up carbon dioxide instead. Your tissues are starving, your organs are failing, and your cardiovascular system, valiant as it is, can't fix what isn't there. Your muscles are starting to accumulate lactic acid. Remember, without oxygen, your cells can only produce ATP through anaerobic glycolysis. And anaerobic glycolysis produces lactic acid as a byproduct. That's the burn you feel during intense exercise when your muscles can't get enough oxygen. Now imagine that burn spreading through your entire body. Your legs, your arms, your chest, even your heart muscle, which never stops working, is accumulating lactic acid. And when the heart becomes too acidic, it stops beating properly. At around the 2-minute mark, most people lose consciousness. Not everyone. Trained freedivers, people with unusually high tolerances for carbon dioxide, people in very cold water where the mammalian dive reflex is strong, they might last a bit longer, but for the average person, 2 minutes without oxygen is the edge. Beyond this point, you're not aware anymore. You're not struggling. You're not panicking. You're just gone. And here's the mercy in that. Once consciousness fades, the suffering stops. You don't feel the continued oxygen starvation. You don't feel your brain dying. You don't feel your heart beginning to fail. There's just silence, darkness, nothing. Your body continues the biological cascade toward death, but you're no longer present to experience it. This is the paradox of suffocation. The worst part isn't the end. The worst part is the middle. The 1 to 2 minutes when you're still awake, still aware, still desperately trying to survive while your body betrays you piece by piece. The burning, the spasms, the tunnel vision, the rising panic, the knowledge that you're drowning in your own carbon dioxide, that your brain is shutting down, and there's nothing, absolutely nothing, you can do to stop it. But once you cross that threshold, once unconsciousness takes you, the struggle ends. And what comes next is quieter, darker, and in some ways far more final. 2 minutes, maybe 2.5, you're unconscious now. The struggle, the panic, the desperate urge to breathe, all of that has faded into silence. Your body is still alive, technically. Your heart is still beating. Blood is still circulating. But you, the conscious you, the part that thinks and feels and experiences the world, you're gone. And this is where the biology gets darker. Because unconsciousness isn't the end. It's just the transition. The moment when your body shifts from crisis management to complete system failure. Here's what's happening inside your skull. Your brain is in full triage mode now. The outer layers, the parts responsible for higher thought, language, memory, and personality, have already started shutting down. Neurons in the cerebral cortex, starved of ATP, are failing one by one. The electrical activity that creates consciousness, that constant hum of coordinated signals firing across billions of synapses, is collapsing. What's left is mostly reflexive activity, brainstem functions, the deep, primitive parts of your nervous system that control things like heart rate, blood pressure, and the faint, sporadic signals still trying to trigger a breath. But even those systems are faltering. Your medulla oblongata, the small region at the base of your brain that's been screaming at your diaphragm to contract, is starting to lose power. The neurons there are dying too. They need oxygen, just like every other cell, and without it, their ability to send signals weakens. The commands become erratic, disorganized, and eventually they stop altogether. This is the point where some people experience what's called agonal breathing. It's not real breathing, not effective breathing. It's more like a reflex, a gasp, a sudden, irregular attempt by the brainstem to force air into the lungs. The chest might heave, the mouth might open, but there's no coordination, no rhythm. It looks violent, desperate, but it's not conscious. And you were in Maimer, and you were in Maimer. It's just the dying nervous system firing one last time, trying to restart a process that's already failed. Now let's talk about what's happening to your brain tissue itself. Without oxygen, without ATP, the sodium-potassium pumps in your neurons have completely stopped working. Remember, these pumps are what maintain the electrical charge across the cell membrane. They keep sodium out and potassium in, creating the voltage difference that allows neurons to fire. But pumps require energy, and energy requires ATP. And ATP requires oxygen. So when oxygen runs out, the pumps fail. And when the pumps fail, the membrane potential collapses. Sodium floods into the cell. The neuron swells with water, a process called cytotoxic edema. The cell membrane, stretched beyond its capacity, becomes unstable. And if this continues for more than a few minutes, the cell ruptures. It dies. permanently. Brain cells don't regenerate. You're born with most of the neurons you'll ever have. And once they're gone, they're gone. No replacement, no recovery, just permanent loss. At around the 3-minute mark, this damage becomes widespread. Entire regions of your brain are experiencing cellular death. The hippocampus, critical for memory formation, is one of the first areas to go. It's exquisitely sensitive to hypoxia. Even a brief period of oxygen deprivation can cause permanent damage there. If you somehow survive this, if oxygen is restored just in time, you might wake up with no memory of what happened, or no ability to form new memories at all. The basal ganglia, involved in movement and coordination, are also vulnerable. Damage here can result in Parkinson's-like symptoms, tremors, rigidity, difficulty initiating movement. The cerebellum, which controls balance and fine motor skills, is another early casualty. Survivors of prolonged hypoxia sometimes struggle to walk, to write, to perform tasks that once felt automatic, because the parts of the brain that made those tasks possible are simply no longer there. Your visual cortex, the region at the back of your brain that processes sight, is dying too. Even if your eyes are open, even if light is still hitting your retinas, there's no one home to interpret the signals. The neurons that turn raw visual data into images, into recognition, into meaning, they're failing. And if they stay oxygen-starved for too long, blindness can be permanent. Not because your eyes are damaged, but because the brain can no longer understand what the eyes are seeing. Meanwhile, your cardiovascular system is starting to unravel. Your heart, which has been working overtime trying to circulate deoxygenated blood, is running out of options. Cardiac muscle cells, like neurons, are extremely energy dependent. They contract constantly, never resting, and that requires a steady supply of ATP. But your coronary arteries, the vessels that supply your heart muscle with oxygenated blood, are delivering less and less oxygen with every passing second. At first, your heart compensates by beating faster, tachycardia. 120 beats per minute, 140, 160. It's trying to move the blood faster, trying to squeeze every last bit of oxygen out of circulation. But speed doesn't fix the underlying problem. The blood is deoxygenated, dark, useless, and eventually the heart muscle itself begins to fail. The electrical system of your heart, the specialized cells that generate and conduct the rhythmic signals that make your heart beat in a coordinated way, starts to malfunction. Normally, your heart beats in a steady pattern. Atria contract, pushing blood into the ventricles. Ventricles contract, pushing blood out to the lungs and body. It's a precise, synchronized dance. But now, oxygen-starved and acidic, the electrical signals become chaotic. You might develop an arrhythmia, ventricular tachycardia, where the ventricles beat too fast to effectively pump blood, or ventricular fibrillation, where the heart muscle quivers uselessly, no longer contracting in any organized way. This is cardiac arrest. Your heart is still moving, technically, but it's not pumping. Blood isn't circulating. And without circulation, the rest of your organs, already starving, begin to shut down completely. Your kidneys stop filtering blood, your liver stops processing toxins, your intestines stop absorbing nutrients, not that it matters now. Every organ system in your body is tied to oxygen delivery, and when oxygen delivery stops, the entire organism begins to collapse. It's not dramatic. There's no explosion, no sudden catastrophic failure, just a quiet, cascading shutdown. one system after another, falling like dominoes. And here's the cruel part. Even if oxygen is restored right now, even if someone performs CPR, even if your heart is restarted and you begin breathing again, the damage might already be irreversible. The brain cells that died in the first 3 to 4 minutes won't come back. The neurons that controlled your memory, your movement, your speech, they're gone. You might survive, but you might not be you anymore. This is why time matters so desperately in cases of cardiac arrest, drowning, or suffocation. Every second counts. Every minute without oxygen pushes you closer to a line you can't come back from.
The medical term is anoxic brain injury.
And it's one of the most devastating outcomes because it doesn't just take your life. It takes your identity, your personality, everything that makes you a conscious, thinking, feeling person. There's a window, roughly 4 to 6 minutes, sometimes a bit longer in cold water, where the mammalian dive reflex and lower body temperature slow metabolism and buy extra time. But in most cases, if oxygen isn't restored within that window, the damage is catastrophic, permanent, final. And even if the heart is restarted, even if breathing resumes, the person who wakes up, if they wake up at all, might be profoundly changed. So here we are, 2 to 3 minutes without oxygen, unconscious, brain cells dying, heart failing, and the countdown continues. Because suffocation doesn't stop at unconsciousness. It keeps going, quiet and relentless, until there's nothing left to shut down. 3 minutes, maybe 3.5. You're past the point where most people lose consciousness. You're deep into the phase where the damage becomes permanent. And now we cross the threshold that neurologists call the point of no return. The moment when brain cells don't just struggle or falter or go quiet, they die, irreversibly, completely. And once a neuron dies, it's gone forever. No regeneration, no repair, just empty space where a functioning cell used to be. Here's why this happens. Brain cells, neurons, are some of the most metabolically demanding cells in your entire body. They consume energy at an astonishing rate. A single cortical neuron can burn through roughly 4.7 billion ATP molecules per second. That's billion with a B. And your brain has approximately 86 billion neurons. The math is staggering. Your brain, which makes up only about 2% of your body weight, uses roughly 20 to 25% of your total oxygen supply. It's an energy hog, and when the energy runs out, it doesn't gracefully power down. It crashes. At the 3-minute mark, ATP levels in your neurons have dropped to nearly zero. The sodium-potassium pumps, which we've talked about before, have been offline for a while now. But now, other critical systems are failing too. Calcium channels in the cell membrane, which are normally tightly regulated, start to malfunction. Calcium ions flood into the neuron, and calcium, in high concentrations, is toxic to cells. Normally, calcium acts as a signaling molecule. It's involved in neurotransmitter release, in synaptic communication, in the electrical activity that makes neurons fire. But calcium needs to be kept at very low levels inside the cell. When it floods in uncontrollably, it triggers a cascade of destructive processes. Enzymes are activated. Proteins are broken down. The mitochondria, those tiny powerhouses inside the cell, are damaged. And the cell begins to digest itself from the inside out. This process is called excitotoxicity, and it's one of the primary mechanisms of neuronal death during hypoxia. Glutamate, the brain's main excitatory neurotransmitter, is released in massive quantities. Normally, glutamate is reabsorbed quickly by surrounding cells, but without ATP, the reuptake pumps don't work.
So, glutamate accumulates in the synaptic space, overstimulating nearby neurons, causing them to fire uncontrollably.
This hyperactivity uses up even more energy, accelerates calcium influx, and spreads the damage to neighboring cells. It's a chain reaction. One dying neuron kills the next, and the next, and the next. Different parts of your brain die at different rates. Some regions are more vulnerable than others.
The hippocampus, a seahorse-shaped structure deep in your temporal lobe, is one of the first to go.
It's critical for forming new memories, for spatial navigation, for learning, and it's incredibly sensitive to oxygen deprivation. Even a few minutes of hypoxia can cause permanent damage here. Survivors of cardiac arrest often wake up with profound memory deficits. They can't remember what happened. They can't form new memories. They live in a perpetual present, unable to encode new experiences. That's hippocampal damage. The cerebral cortex, the wrinkled outer layer of your brain responsible for higher cognitive functions, is also highly vulnerable. The neurons here are packed densely, firing constantly, consuming energy at a breakneck pace. When oxygen disappears, they're some of the first to die. And because different regions of the cortex control different functions, the pattern of damage determines what abilities are lost. Damage to the frontal lobe might affect personality, decision-making, impulse control. Damage to the parietal lobe might impair spatial awareness, the ability to understand where your body is in space. Damage to the temporal lobe affects language, memory, auditory processing. Damage to the occipital lobe causes blindness, even though the eyes themselves are fine. The cerebellum, tucked under the back of your brain, is another early casualty. It coordinates movement, balance, fine motor control. Survivors of severe hypoxia sometimes develop ataxia, a condition where movements become jerky, uncoordinated, clumsy. They can't walk in a straight line. They can't touch their nose with their finger. Their handwriting becomes illegible, because the part of the brain that made those movements smooth and automatic is no longer functioning. But here's the strange thing. Not all parts of the brain die at the same rate. The brainstem, the most primitive part of your brain, is remarkably resistant to hypoxia. It can survive longer than the cortex, longer than the hippocampus, longer than almost any other region. This is why someone can be brain dead, with no higher brain function, no consciousness, no awareness. But their heart is still beating and they're still breathing with the help of a ventilator. The brainstem, which controls those basic life support functions, is still alive. But the person, the personality, the self, is gone. This creates a tragic situation. A body that's technically alive, but a mind that's been erased. Doctors call this a persistent vegetative state. The eyes might open, the body might move reflexively, but there's no one home. The parts of the brain that create consciousness, that generate thought and feeling and identity, have been destroyed, and they're not coming back. At around the 4-minute mark, the damage is catastrophic. Large swaths of your cerebral cortex are dead. Your hippocampus is gone. Parts of your cerebellum, your basal ganglia, your thalamus, all critical structures, are experiencing widespread cell death. And even if oxygen is restored now, even if your heart is restarted and blood begins flowing again, the outcome is grim. You might survive, but you won't be the same. You might not recognize your family. You might not be able to speak, or walk, or feed yourself. You might spend the rest of your life in a care facility, aware but diminished, or unaware entirely. This is why neurologists are so obsessed with time when it comes to stroke, cardiac arrest, or any event that cuts off oxygen to the brain.
There's a phrase in emergency medicine: time is brain. Every minute that passes without oxygen, roughly 2 million neurons die. 2 million.
And the brain contains roughly 86 billion neurons total. Do the math. After just 10 minutes, you've lost 20 million neurons. After 20 minutes, 40 million. The damage accumulates exponentially. And there's no surgery, no drug, no treatment that can bring those neurons back. There are some exceptions. Rare cases. Children who fall through ice into freezing water and are submerged for 20, 30, even 40 minutes. They're pulled out. No pulse, no breathing, clinically dead. But because the water was so cold, their body temperature dropped rapidly. Hypothermia slowed their metabolism, their brain needed less oxygen, and somehow, miraculously, they survived, with full neurological recovery. These cases are extraordinary. They're the edge cases that rewrite the rules. But they're also vanishingly rare. For most people, in most situations, 4 minutes without oxygen is the line. Cross it, and the damage is permanent. The neurons that controlled your memories, your movements, your ability to think and reason and feel, they're gone. You might live, but you won't be you. And that, in many ways, is a fate worse than death, because the body survives, but the person inside it has been erased. So here we are, 3 to 4 minutes without oxygen. The brain, that 3-pound organ that makes you who you are, is dying. Piece by piece, neuron by neuron, and the countdown continues, because even as the brain fails, the body isn't done yet. The heart is still struggling, the organs are still shutting down, and the final collapse, the moment when everything stops, is coming soon. 4 minutes, maybe closer to 5. Your brain is dying. Large regions of it are already gone, neurons ruptured and silent, leaving gaps in the tissue that will never be filled. But your heart, that tireless muscle in the center of your chest, is still fighting, still beating, or trying to. Because while the brain gives up quickly when oxygen disappears, the heart is more stubborn, more resilient. It has to be. It's been beating since before you were born, contracting roughly once every second for your entire life, and it doesn't know how to stop until it does. Here's what you need to understand about your heart. It's not just a pump, it's an electrical system wrapped in muscle. The rhythm you feel when you check your pulse, that steady thump thump, thump thump, is the result of coordinated electrical signals traveling through specialized cardiac cells. These signals start in a small cluster of cells called the sinoatrial node, located in the right atrium. The SA node is your heart's natural pacemaker. It fires automatically, roughly 60 to 100 times per minute, sending an electrical impulse that spreads across both atria, causing them to contract and push blood into the ventricles. The signal then reaches the atrioventricular node, another cluster of specialized cells, which delays the impulse just long enough for the atria to finish contracting. Then the signal races down the bundle of His, splits into the left and right bundle branches, and spreads through the Purkinje fibers, causing the ventricles to contract from the bottom up, squeezing blood out into your lungs and the rest of your body. It's a beautifully orchestrated process. Electrical signal, mechanical contraction, blood flow over and over and over, 3 billion times in an average lifetime. But this system, elegant as it is, requires energy, ATP, and ATP requires oxygen. The cells in your heart muscle, called cardiomyocytes, are packed with mitochondria, more mitochondria than almost any other cell type in your body. Because cardiac muscle never rests. It can't afford to. One skipped beat could mean disaster. So your heart has evolved to be an energy production powerhouse. But even powerhouses need fuel, and right now, the fuel is gone. At the 4-minute mark, your coronary arteries, the blood vessels that supply your heart muscle with oxygenated blood, are delivering essentially nothing. The blood flowing through them is dark, deoxygenated, useless. Your cardiomyocytes are running on whatever ATP reserves they had left, which isn't much. And as those reserves deplete, the muscle cells start to fail. Not all at once, but gradually, unevenly, creating a dangerous patchwork of functioning and non-functioning tissue. This is where arrhythmias begin. An arrhythmia is any deviation from the normal heart rhythm, and when your heart is oxygen-starved, arrhythmias become almost inevitable. The electrical signals that normally travel smoothly through your cardiac tissue start encountering dead zones, cells that can't conduct the signal, cells that are firing randomly, chaotically, out of sync with the rest of the heart. The result is electrical chaos. One of the first arrhythmias to develop is ventricular tachycardia. This is when the ventricles, the lower chambers of your heart, start beating extremely fast. 150 beats per minute, 200, 250. At that speed, the ventricles don't have time to fill with blood between contractions. So even though your heart is beating, it's not pumping effectively. Blood pressure drops, circulation falters, and your brain, already dying, gets even less oxygen, which accelerates the damage, which stresses the heart further. It's a vicious cycle. But ventricular tachycardia can get worse. It can degrade into ventricular fibrillation, and this is where things become truly catastrophic. In ventricular fibrillation, the ventricles don't contract at all, they quiver. The muscle fibers twitch randomly, independently, with no coordination. Imagine a room full of people all clapping at different times, completely out of sync. That's what your heart muscle is doing. And when the ventricles are fibrillating, they're not pumping blood at all. Blood flow stops, circulation ceases, and you are, for all practical purposes, dead. This is cardiac arrest, not a heart attack, which is when blood flow to the heart muscle is blocked. Cardiac arrest is when the heart stops beating effectively. And once you're in ventricular fibrillation, the only way to restore a normal rhythm is with a defibrillator. An electric shock strong enough to reset the heart's electrical system, to stop all the chaotic firing, and hopefully allow the SA node to take over again. But if there's no defibrillator, if there's no one to perform CPR, if you're alone or in a situation where help can't reach you, ventricular fibrillation is terminal. Your heart will continue to fibrillate for a few minutes, burning through the last of its energy reserves, and then it will stop moving entirely. Asystole, flatline, the end. Even if your heart hasn't reached full fibrillation yet, the muscle itself is dying. Cardiac cells, like neurons, are incredibly sensitive to oxygen deprivation. After about 4 to 5 minutes without oxygen, cardiomyocytes begin to undergo irreversible damage. The mitochondria swell, the cell membranes rupture, enzymes leak out into the surrounding tissue, causing inflammation and further damage. This is called myocardial necrosis. Heart, muscle, death. And unlike skeletal muscle, which can regenerate to some extent, cardiac muscle doesn't grow back. Once it's dead, it's replaced by scar tissue. Tough, fibrous, non-contractile scar tissue that doesn't help pump blood. It just sits there, a permanent reminder of the damage. Now, here's something most people don't realize. Your heart can keep beating even after you're brain dead. Even after consciousness is gone, even after higher brain function has ceased, the brainstem can still send signals to the heart. Or the heart, which has its own intrinsic rhythm, can keep contracting on its own. This is why you sometimes hear about people who are declared brain dead, but their heart is still beating, the body is alive, the organs are functioning. But the person, the mind, the self is gone. It's one of the most unsettling realities of modern medicine. The line between life and death isn't as clear as we'd like to think. But in true suffocation, where oxygen is completely absent and no intervention occurs, the heart doesn't last long. 5 minutes, maybe 6. The electrical system fails. The muscle stops contracting, blood stops circulating. And when circulation stops, every other organ in your body begins to die too. Your kidneys, which filter roughly 200 liters of blood every day, stop functioning. Your liver, which detoxifies your blood and produces essential proteins, shuts down. Your intestines, your pancreas, your lungs, even though they're no longer breathing, all of these organs depend on oxygenated blood. And without it, they begin to necrose, to die, to rot, essentially, while still inside your body. This is systemic organ failure, and it's irreversible. You can restart a heart with CPR and a defibrillator. You can restore breathing with a ventilator. But you can't bring back organs that have been without oxygen for this long. The damage is too extensive. The tissue is too far gone. Even if the heart is restarted, even if circulation is restored, the kidneys might never filter blood again. The liver might never detoxify. The intestines might never absorb nutrients. The person might survive, technically, but only with dialysis, with transplants, with machines doing the work that their organs can no longer do. And through all of this, the heart, your loyal, tireless, never-resting heart, is doing everything it can to keep going. It's failing, yes. It's dying, absolutely. But it's still trying, still firing signals, still contracting, even weakly, even chaotically, because the heart doesn't know how to give up. It's been programmed, through millions of years of evolution, to keep beating no matter what, to fight until the very last spark of energy is gone. But that spark is fading now. The ATP is gone, the oxygen is gone, the electrical system is collapsing, and in the next minute or two, the heart will make its final contractions, weaker and slower with each beat, until it stops altogether. And when it stops, when that last beat fades into silence, the story of suffocation reaches its inevitable end. 5 minutes, maybe pushing toward 10, your brain is mostly gone. Your heart has stopped, or it's barely twitching in its final moments of disorganized electrical activity. And now the rest of your body, the organs and systems that have been struggling in the background this entire time, begin their final collapse. This is systemic failure, not the dramatic, explosive kind you see in movies, but a quiet, cascading shutdown, one organ system after another falling silent as the absence of oxygen spreads through your body like a slow tide. Let's start with your kidneys. You have 2 of them, bean-shaped organs tucked against your lower back, each about the size of your fist. And their job, every single day, is nothing short of extraordinary. They filter your entire blood volume, roughly 5 liters, about 30 to 40 times per day. That's around 200 liters of blood passing through your kidneys daily. They remove waste products, excess water, toxins, anything your body doesn't need, and turn it into urine. They also regulate your blood pressure, balance electrolytes, and produce hormones that stimulate red blood cell production. They're chemical factories, constantly working, constantly adjusting, constantly filtering. But all of that activity requires energy, massive amounts of it. Your kidneys consume about 7% of your body's total oxygen supply, even though they represent less than 1% of your body weight. They're second only to your brain and heart in terms of energy demand per gram of tissue. And that energy comes from ATP, produced in the mitochondria of kidney cells through aerobic respiration. Oxygen in, ATP out. Always. Constantly. Until now. At the 5-minute mark without oxygen, your kidneys have stopped filtering. The cells lining the tiny tubules inside each kidney, the nephrons where the actual filtration happens, have run out of ATP. The sodium-potassium pumps that move ions and create the concentration gradients necessary for filtering, they've failed. The cells swell. The membranes rupture. And the nephrons, roughly 1 million per kidney, begin to die. Acute tubular necrosis, it's called. The tubules are necrotizing, dying, turning into dead, useless tissue. If circulation were restored right now, if oxygen somehow returned, your kidneys might recover. Partially, the damage might be reversible with dialysis, with time, with medical intervention. But if the oxygen deprivation continues, the damage becomes permanent. Total renal failure. Your blood would fill with toxins, with urea, with creatinine, with potassium, all the waste products your kidneys are supposed to remove. And without dialysis, without a transplant, that buildup would kill you within days. Though at this point, it's irrelevant, because your brain is already gone. Next, your liver, the largest internal organ in your body, weighing about 3 pounds and sitting just below your rib cage on the right side. Your liver is a biochemical marvel. It performs over 500 different functions. It detoxifies your blood, removing alcohol, drugs, and metabolic waste. It produces bile to help digest fats. It stores glucose as glycogen and releases it when your blood sugar drops. It synthesizes proteins, including clotting factors that stop you from bleeding to death when you're injured. It breaks down old red blood cells. It regulates cholesterol. It's a chemical processing plant running 24 hours a day, 7 days a week, without ever taking a break. And like your kidneys, your liver is incredibly energy hungry. It consumes roughly 20% of your total oxygen supply. The hepatocytes, the main functional cells of the liver, are packed with mitochondria. They need to be, because every chemical reaction the liver performs, every molecule it synthesizes or breaks down, requires energy, requires ATP, requires oxygen. And right now, there is none. Hepatocytes are surprisingly resilient. They can tolerate hypoxia better than neurons or cardiomyocytes, but only for a limited time. After 5 to 10 minutes without oxygen, they start to die. The cell membranes break down, enzymes leak out into the bloodstream. If you were to test the blood of someone who's been oxygen deprived for this long, you'd see elevated levels of liver enzymes, AST, ALT, markers of hepatocellular injury. The liver is dying, and when the liver fails, toxins accumulate, ammonia levels rise, bilirubin, a breakdown product of hemoglobin, builds up, turning the skin and eyes yellow. Jaundice. Hepatic encephalopathy, where toxins cross into the brain and cause confusion, seizures, coma. Though again, at this point, the brain is already too damaged to care. Your pancreas is failing too. This small, unassuming organ tucked behind your stomach has two main jobs. It produces digestive enzymes that break down food in your intestines, and it produces hormones, insulin and glucagon, that regulate your blood sugar. Without oxygen, the enzyme-producing cells, the acinar cells, begin to die. The hormone-producing cells, clustered in the islets of Langerhans, fail as well. Blood sugar regulation collapses. Insulin production stops. Glucagon secretion becomes erratic. If you were somehow kept alive, you'd develop diabetes, acute pancreatitis, digestive dysfunction. But you're not alive, not in any meaningful sense. Your intestines, that long, coiled tube stretching from your stomach to your rectum, roughly 25 feet in total length, are also shutting down. The lining of your intestines, the epithelial cells that absorb nutrients and water, are among the fastest dividing cells in your body. They regenerate completely every 3 to 5 days, but that rapid turnover requires energy, lots of it. And without oxygen, the cells stop dividing. They stop absorbing. They start sloughing off into the intestinal lumen, leaving the inner wall raw, exposed, vulnerable. Worse, the tight junctions that normally keep the intestinal barrier intact, preventing bacteria from your gut from entering your bloodstream, those junctions break down. Bacteria leak through. Toxins leak through. If your heart was still beating, if circulation was still happening, those bacteria would seed into your blood and cause sepsis, a life-threatening systemic infection. But your heart has stopped. Your blood isn't circulating. So the bacteria just sit there, multiplying in the dying tissue, beginning the process of decomposition from the inside out. Your spleen, your adrenal glands, your thyroid, every organ in your body that depends on oxygenated blood, and that's all of them, is experiencing the same fate. Cells are dying, tissue is necrotizing, function is ceasing, and there's no coming back from this. Even if oxygen were restored, even if your heart were restarted and your lungs began breathing again, the damage is too extensive. Too many organs have failed, too much tissue has died. The body, as a functional organism, is finished. But here's the strange part. Even now, even with all of this catastrophic failure happening simultaneously, some cells are still alive. Your skin cells, for example. They're far from your core, far from your brain and heart, and they have a relatively low metabolic rate. They can survive hypoxia longer than most other cell types. Hours, in some cases. Your hair follicles, your nails, these structures continue growing for a short time, even after death, because they're not dependent on a constant supply of oxygenated blood. They're running on residual nutrients, on whatever ATP they had stored, on the last traces of energy left in the system. This is why organ transplantation is possible. Why doctors can harvest kidneys, livers, hearts, lungs from someone who's been declared dead and transplant them into someone else. Because those organs, even though the person is gone, are still viable. For a little while, the cells are still intact. The tissue is still functional. If you can get it into a new body quickly enough, restore blood flow, deliver oxygen, the organ can come back to life. But the window is narrow. Minutes for the heart, hours for the kidneys and liver. Beyond that, the damage is irreversible. So here we are, 5 to 10 minutes without oxygen. Your brain is dead, your heart is silent. Your organs are failing, necrotizing, dissolving into useless tissue. The organism that was you, the living, breathing, thinking, feeling human being, no longer exists. What's left is a biological artifact, a collection of cells and tissues and organs that used to work together, that used to support consciousness, that used to be a person, but not anymore. Now it's just chemistry, entropy, the slow, inevitable breakdown of order into chaos. And that process, once it starts, doesn't stop. It only accelerates until nothing remains but the elements you were made from. So far, we've talked about suffocation in the abstract, the general biology of oxygen deprivation. But suffocation doesn't happen in a vacuum. It happens in specific situations, and one of the most common, most terrifying, and most misunderstood forms of suffocation is drowning. Not the Hollywood version, where someone thrashes dramatically for minutes before sinking gracefully beneath the waves. Real drowning, the kind that kills more than 320,000 people worldwide every year. And the biology of it, the way your body responds when water replaces air, is more complex and more fascinating than you might think. Let's start with the moment of submersion. You're underwater. Maybe you slipped, maybe you panicked, maybe you misjudged the depth or got caught in a current. Doesn't matter. What matters is that your head is below the surface and you need to breathe. But you can't, because there's no air, just water. And your body, which has been breathing automatically for your entire life, suddenly doesn't know what to do. The first thing that happens, assuming you didn't inhale immediately upon going under, is breath holding. Your larynx, the structure in your throat that houses your vocal cords, clamps shut. This is an involuntary reflex called laryngospasm. It's designed to protect your airway, to prevent water from entering your lungs, and for a while it works. You're underwater, desperate for air, but your throat is sealed. No water gets in, but no air gets in either, and the clock starts ticking. Now, here's where things get interesting. The type of water you're drowning in, fresh water or salt water, makes a significant difference in what happens next. And the biology behind this difference is both elegant and brutal. Let's start with fresh water. Lakes, rivers, pools. Most drownings happen in fresh water. And when fresh water enters your lungs, which it eventually will once the laryngospasm breaks, it does something very specific. It gets absorbed. Your alveoli, those tiny air sacs where gas exchange normally happens, are surrounded by capillaries, and the walls separating the alveoli from the bloodstream are incredibly thin enough that oxygen and carbon dioxide can pass through easily, but also thin enough that water can pass through. And fresh water, because it has a lower concentration of dissolved salts and solutes than your blood, moves across that membrane quickly. It floods into your bloodstream, and this causes a cascade of problems. First, your blood volume increases, suddenly, dramatically. Your heart, already stressed from oxygen deprivation, now has to pump more blood. But it's not just more blood. It's diluted blood. The concentration of electrolytes, sodium, potassium, chloride, drops rapidly. This condition is called hemodilution, and it's dangerous. Your red blood cells, suspended in this suddenly hypertonic environment, start to swell. Water rushes into them, trying to equalize the concentration gradient, and if they swell too much, they burst. Hemolysis, it's called. The rupture of red blood cells. When red blood cells rupture, they release their contents into the bloodstream. Hemoglobin, potassium, all of it spills out. And free hemoglobin in the bloodstream is toxic. It can damage your kidneys, clog the tubules, cause acute renal failure. Meanwhile, the sudden spike in potassium, hyperkalemia, can trigger fatal cardiac arrhythmias. Your heart, already struggling, is now being bombarded with electrical chaos, ventricular fibrillation, cardiac arrest, death. But saltwater drowning is different. Ocean water, seawater, has a much higher concentration of dissolved salts than your blood. It's hypertonic. So when salt water enters your alveoli, it doesn't get absorbed into your bloodstream. Instead, it does the opposite. It pulls water out of your blood. Plasma, the liquid component of your blood, moves across the alveolar membrane into your lungs. Your blood becomes thicker, more concentrated. Hemoconcentration. Your blood volume drops. Your blood pressure plummets. And your heart, trying to pump increasingly viscous blood through your arteries, struggles even more. At the same time, your alveoli are filling with fluid. Not just the seawater you inhaled, but also the plasma being pulled from your bloodstream. This is pulmonary edema. Your lungs are drowning from the inside out. The surface area available for gas exchange shrinks rapidly. Oxygen can't cross into your blood because the alveoli are flooded. And even if you're rescued, even if you're pulled from the water and start breathing again, the fluid in your lungs can take hours to clear. People have drowned on dry land hours after being pulled from the ocean because their lungs were so full of fluid they couldn't oxygenate their blood. But there's something else, something your body does, an ancient reflex, left over from our evolutionary past, that can sometimes save your life. It's called the mammalian dive reflex, and it's triggered when cold water hits your face. Specifically, the receptors around your nose, mouth, and eyes. When those receptors detect cold water, they send signals to your brainstem, and your brainstem responds by doing three things simultaneously. First, your heart rate slows dramatically. Bradycardia, from 60 or 70 beats per minute down to 30, 20, sometimes even lower. This seems counterintuitive. Your body needs oxygen desperately, so why would your heart slow down? Because a slower heart uses less oxygen, it conserves the limited supply that's left. Second, blood vessels in your extremities constrict, peripheral vasoconstriction. Blood is redirected away from your arms, legs, and skin and shunted toward your core, toward your heart, lungs, and most importantly, your brain. The goal is to keep the most vital organs alive for as long as possible. Third, your spleen contracts. You have a spleen, a fist-sized organ tucked under your ribcage on the left side, and one of its jobs is to store red blood cells. When the dive reflex is triggered, your spleen squeezes, releasing those stored red blood cells into your circulation. More red blood cells means more oxygen-carrying capacity. It's a biological emergency reserve, and in some cases, it's enough to buy an extra minute or two, enough to make the difference between life and death. This reflex is strongest in infants and young children. It's why there are stories of toddlers who fall into icy ponds, are submerged for 10, 15, even 20 minutes, and survive with minimal brain damage. The cold water triggers the dive reflex. Their heart rate plummets, their metabolism slows. Their brain, cooled by the cold water, needs less oxygen, and somehow, miraculously, they survive. These cases are rare, extraordinary, but they happen, and they've taught us that the old rules about brain death after 4 to 6 minutes They're not absolute. Under the right conditions, cold water, youth, a strong dive reflex, the window can be longer. But for most people, in most drowning situations, the dive reflex isn't enough. The water is too warm. The panic overrides the reflex. The submersion lasts too long, and the outcome is the same as any other form of suffocation: oxygen deprivation, unconsciousness, brain damage, cardiac arrest, death. The only difference is the mechanism, the path the body takes to get there. But the destination is the same. And here's the cruelest part. Drowning is often silent. People don't scream, they don't wave their arms, they don't call for help, because calling for help requires breath. And if you're drowning, you don't have breath to spare. Your body is too busy trying to keep your head above water, trying to gulp air whenever your mouth breaks the surface, to waste energy on anything else. So, drowning looks like someone treading water quietly, vertically, head tilted back, mouth opening and closing, no sound, no splashing, just a desperate, silent struggle that can be over in less than a minute. This is why drowning happens so often in crowded pools, at beaches with lifeguards on duty, in situations where help is nearby but no one realizes what's happening. Because drowning doesn't look like drowning. It looks like nothing until the person slips beneath the surface and doesn't come back up. Drowning is sudden, violent, a rapid plunge into oxygen deprivation. But there's another form of suffocation that's slower, quieter, and in some ways more insidious. It happens on mountains, at high altitudes, where the air is thin and every breath feels like it's not quite enough. This is hypoxia by degrees, suffocation in slow motion. And it reveals something fascinating about how your body responds when oxygen is available, just not enough of it. Let's start with the basics. At sea level, the air you breathe is roughly 21% oxygen. The atmospheric pressure is around 760 millimeters of mercury, and that pressure is what drives oxygen from your lungs into your bloodstream. Think of it like a gradient. High pressure outside, lower pressure inside your blood. Oxygen flows down that gradient, crosses the alveolar membrane, binds to hemoglobin, and gets carried away. It's passive. It's automatic. It works perfectly as long as the pressure difference is sufficient. But as you climb higher, atmospheric pressure drops. At the summit of Mount Everest, roughly 29,000 feet above sea level, the atmospheric pressure is only about a third of what it is at sea level. The air still contains 21% oxygen. The ratio hasn't changed, but the total number of oxygen molecules per breath has dropped dramatically. You're breathing the same volume of air, but you're getting far less oxygen with each inhale, and your body notices. At around 8,000 feet, most people start to feel it. A slight shortness of breath, maybe a mild headache, fatigue that seems disproportionate to the activity you're doing. This is the beginning of altitude sickness or acute mountain sickness. It's your body's way of saying, something is wrong. We're not getting enough oxygen. And if you ignore those early warning signs, if you keep climbing without giving your body time to adapt, things get worse. Here's what's happening physiologically. Your chemoreceptors, those sensors in your carotid arteries and brainstem that monitor blood oxygen and carbon dioxide levels, detect the drop in oxygen saturation, and they respond by increasing your respiratory rate. You start breathing faster, deeper, trying to pull in more oxygen with each breath. This is called hyperventilation, and in the short term, it helps. More breaths per minute means more oxygen entering your lungs, even if each breath contains less oxygen than it would at sea level. But hyperventilation creates a new problem. When you breathe faster, you exhale more carbon dioxide. And carbon dioxide is what regulates your blood pH. When you blow off too much carbon dioxide, your blood becomes more alkaline. Respiratory alkalosis, it's called, and your body doesn't like that either. The alkaline environment affects enzyme function, nerve signaling, muscle contraction. You might feel dizzy, lightheaded, tingly in your fingers and toes. Your muscles might cramp. It's a balancing act. Your body is trying to get more oxygen while not disrupting blood chemistry too much. And at moderate altitudes, it usually manages. But at extreme altitudes, above 18,000 or 20,000 feet, the balance becomes impossible. No amount of hyperventilation can compensate for the lack of oxygen. Your blood oxygen saturation, which should be 95 to 100% at sea level, drops to 70%, 60%, 50%, and your body, starved for oxygen, begins to fail. Not quickly, like in drowning or choking, but gradually, over hours or days. A slow suffocation. One of the most dangerous complications is high-altitude pulmonary edema, HAPE. This is when fluid leaks from your capillaries into your alveoli, the same thing that happens in saltwater drowning, but for a different reason. At high altitude, the low oxygen levels cause the blood vessels in your lungs to constrict. Hypoxic pulmonary vasoconstriction, it's called. The body's attempt to redirect blood flow to better ventilated parts of the lung, but this constriction increases pressure in the pulmonary capillaries. And if the pressure gets high enough, fluid is forced out of the blood vessels and into the alveoli. Your lungs start to fill with fluid. You develop a cough, a wet, rattling cough. You might cough up pink, frothy sputum, a mixture of fluid and blood. Breathing becomes labored. Your oxygen saturation drops even further. And if you don't descend immediately, if you don't get to lower altitude where your lungs can clear, you drown in your own fluids on a mountaintop, surrounded by air. Then there's high-altitude cerebral edema, HACE. This is even more deadly. It's brain swelling caused by hypoxia. The exact mechanism isn't fully understood, but the leading theory is that low oxygen levels cause the blood-brain barrier to become leaky. Fluid seeps from your capillaries into your brain tissue. Your brain, encased in your rigid skull, has nowhere to expand. So the pressure inside your skull increases, intracranial pressure. And as the pressure rises, it compresses brain tissue, cutting off blood flow, causing further hypoxia, creating a vicious cycle. The symptoms are terrifying: severe headache, confusion, ataxia, an inability to walk in a straight line, hallucinations, seizures, and eventually coma. If you don't descend immediately, if you don't reduce the altitude and the hypoxia, your brain will herniate. The pressure will force brain tissue down through the opening at the base of your skull, the foramen magnum, compressing your brainstem. And when your brainstem is compressed, the centers that control breathing and heart rate stop working. You stop breathing. Your heart stops. You die. But here's the fascinating part. Some people adapt. Given enough time, your body can acclimatize to high altitude. It's not a quick process. It takes days, sometimes weeks, but your body makes adjustments. Your breathing rate stays elevated, even at rest, increasing oxygen intake. Your heart rate increases, speeding up circulation. Your kidneys adjust, excreting bicarbonate to compensate for the respiratory alkalosis. And most importantly, your bone marrow ramps up production of red blood cells. This is driven by a hormone called erythropoietin. or EPO. When your kidneys detect low oxygen levels in the blood, they release EPO. And EPO travels to your bone marrow and signals it to produce more red blood cells. More red blood cells means more hemoglobin. More hemoglobin means more oxygen carrying capacity. Over the course of a few weeks at high altitude, your red blood cell count can increase by 20 to 30%. Your blood becomes thicker, richer, more efficient at capturing and delivering oxygen. This is why elite endurance athletes sometimes train at high altitude, or why some athletes, unethically, inject synthetic EPO. Because more red blood cells means better oxygen delivery. Better oxygen delivery means better performance. Your muscles can work harder, longer, before they run out of oxygen and switch to anaerobic metabolism. It's a biological advantage. Though it comes with risks, thicker blood is harder to pump. It increases the risk of blood clots, strokes, heart attacks. Evolution didn't design us to live at 20,000 feet, and the adaptations that allow us to survive there come with trade-offs. People who are born and raised at high altitude, populations in the Andes, the Himalayas, the Tibetan Plateau, they've adapted over generations. Their bodies are more efficient at extracting oxygen from thin air. Tibetans, for example, have higher resting ventilation rates and more efficient oxygen utilization at the cellular level. Andean populations have higher hemoglobin concentrations. These are genetic adaptations honed over thousands of years of living in low oxygen environments. But for the rest of us, for lowlanders who venture into the mountains without proper acclimatization, high altitude is hostile, dangerous, potentially fatal. And the cruelest part? High altitude hypoxia impairs judgment. As your brain becomes oxygen starved, your decision-making deteriorates. You become confused, euphoric, even. Some climbers, suffering from severe hypoxia near the summit of Everest, report feeling warm and comfortable even as they're freezing to death. They remove their gloves, their jackets, because they feel hot. This is called paradoxical undressing. It's a sign of severe hypothermia combined with hypoxia. The brain is so dysfunctional that it can no longer interpret sensory information correctly. You might not realize you're in danger. You might not recognize the symptoms of HAPE or HACE until it's too late. You might make decisions that seem reasonable in the moment, but are objectively suicidal. Continuing to climb when you should descend. Ignoring warning signs. Pushing through symptoms. Because your brain, the organ responsible for keeping you alive, is the first to fail when oxygen runs low. And once it starts failing, you can't trust it to save you. So, high altitude teaches us something important about suffocation. It doesn't always happen in seconds or minutes. Sometimes it happens slowly, quietly, degree by degree, your body fighting, adapting, compensating until it simply can't anymore. And by the time you realize how much danger you're in, you're already too hypoxic to do anything about it. There's another kind of suffocation, one that doesn't involve water or altitude or any obvious threat. You're breathing normally. Your lungs are filling with air. Your respiratory rate is fine, but you're suffocating anyway, slowly, invisibly, without ever knowing it's happening. This is carbon monoxide poisoning. And it's one of the most insidious ways to die because your body's alarm systems, the ones that scream at you when carbon dioxide builds up or oxygen drops, they stay completely silent. You suffocate while breathing normally. And you never feel a thing. Let's talk about carbon monoxide. It's a gas, colorless, odorless, tasteless. completely undetectable by human senses. It's produced whenever carbon-based fuel burns incompletely. Car engines, gas furnaces, wood stoves, portable generators, charcoal grills. Any combustion process that doesn't have enough oxygen produces carbon monoxide, and if that carbon monoxide accumulates in an enclosed space, a garage, a house, a tent, it becomes deadly. Not because it's toxic in the traditional sense, but because it hijacks the one molecule your body depends on to carry oxygen, hemoglobin. Remember hemoglobin, that protein inside your red blood cells, shaped like a four-leaf clover with 4 binding sites for oxygen. Hemoglobin's job is to grab oxygen in your lungs, hold onto it as blood circulates through your body, and release it to cells that need it. It's extraordinarily good at this job. The binding affinity, the chemical attraction between hemoglobin and oxygen, is perfectly calibrated, strong enough to pick up oxygen in the high-pressure environment of your lungs, weak enough to release it in the low-pressure environment of your tissues. But hemoglobin has a weakness, a fatal flaw. It binds to carbon monoxide even more strongly than it binds to oxygen, roughly 200 to 250 times more strongly. So, if you're breathing air that contains both oxygen and carbon monoxide, even a tiny amount of carbon monoxide, your hemoglobin preferentially binds the carbon monoxide, and once carbon monoxide is bound, it doesn't let go. The bond is so tight, so stable, that the hemoglobin molecule is essentially locked, occupied, useless for oxygen transport. This is called carboxyhemoglobin, hemoglobin that's carrying carbon monoxide instead of oxygen. And here's the terrifying part. You can be breathing air with plenty of oxygen in it, 21% oxygen, normal atmospheric levels. But if even a small fraction of that air is carbon monoxide, your hemoglobin will prioritize the carbon monoxide. Your oxygen carrying capacity drops. Not because there's no oxygen, but because your hemoglobin is occupied, bound to the wrong molecule. At low levels of carbon monoxide exposure, you might not notice anything. Maybe a mild headache, a little fatigue, easy to dismiss, easy to attribute to stress or lack of sleep. But your blood oxygen delivery is already compromised. Your cells are getting less oxygen than they need. Your brain, your heart, your muscles, all of them are running on reduced fuel. And as the exposure continues, as more and more hemoglobin molecules bind carbon monoxide, the symptoms worsen. Confusion, dizziness, nausea, weakness. Your vision might blur, your coordination might falter. You might feel like you're coming down with the flu. And because these symptoms are so nonspecific, because they mimic so many other conditions, people often don't realize they're being poisoned. They lie down to rest, they go to sleep, and they never wake up. Because while they're unconscious, the carbon monoxide keeps accumulating. Their carboxyhemoglobin levels keep rising, and their oxygen delivery keeps dropping until it's insufficient to sustain life. Here's what makes carbon monoxide poisoning so cruel. Your chemoreceptors, the sensors that monitor your blood chemistry and trigger the urge to breathe, they don't detect low oxygen directly. They detect high carbon dioxide, and carbon dioxide levels are fine. You're breathing normally, exhaling carbon dioxide just fine. So your chemoreceptors don't sound the alarm. You don't feel short of breath. You don't gasp. You don't panic. You just slowly, quietly lose consciousness as your brain is starved of oxygen. At a carboxyhemoglobin level of 10 to 20%, you develop headaches and mild cognitive impairment. At 20 to 30%, severe headache,
nausea, impaired judgment. At 30 to 40%, confusion, visual disturbances, collapse. At 50% or higher, seizures, coma, death. And you can reach those levels faster than you think. In a closed garage with a running car, carbon monoxide concentrations can become lethal within minutes. In a house with a malfunctioning furnace, it might take hours. But the end point is the same. Now, let's talk about what's happening at the cellular level. Your cells are being deprived of oxygen, not because oxygen isn't in your lungs, not because your lungs aren't working, but because the oxygen can't be delivered. It's like having a fleet of delivery trucks that are all full but all headed to the wrong address. The oxygen is there. It's just not getting where it needs to go. And without oxygen, your mitochondria can't produce ATP. Cellular respiration fails. Neurons stop firing. Cardiomyocytes stop contracting. The sodium-potassium pumps fail. The whole cascade we've already discussed, it all happens again. Except this time, you never knew you were in danger. But carbon monoxide does something else. Something beyond just blocking oxygen transport. It directly damages cells. Carbon monoxide binds to proteins other than hemoglobin. It binds to myoglobin, the oxygen storage protein in your muscles. It binds to cytochrome C oxidase, a critical enzyme in the electron transport chain inside your mitochondria. By binding to cytochrome C oxidase, carbon monoxide directly inhibits ATP production at the cellular level. Even if some oxygen manages to reach your cells, they can't use it efficiently. The machinery is broken. This is why carbon monoxide poisoning can cause long-term damage even if you survive. Even if you're removed from the carbon monoxide source, even if your carboxyhemoglobin levels return to normal, the cellular damage persists. People who survive severe carbon monoxide poisoning often develop neurological problems weeks or months later. Memory loss, personality changes, movement disorders, because the neurons that were damaged during the acute poisoning don't fully recover. The mitochondria were injured, the cells were starved, and some of them died, permanently. There's a treatment, hyperbaric oxygen therapy. You're placed in a pressurized chamber and given pure oxygen to breathe. The high pressure and high oxygen concentration help displace carbon monoxide from hemoglobin, speeding up its elimination from your body. Normally, it takes 4 to 6 hours for half the carbon monoxide in your blood to dissociate naturally. With hyperbaric oxygen, that time drops to about 20 minutes, and the sooner you get treatment, the better the outcome. But you have to know you've been poisoned. You have to recognize the symptoms, and often people don't. Carbon monoxide detectors exist for this reason. Small devices that sound an alarm when carbon monoxide levels reach dangerous concentrations. They're cheap, effective, life-saving, but not everyone has them, and even when they do, people sometimes ignore them. Assume it's a false alarm, turn them off, go back to sleep, and that decision can be fatal. Because carbon monoxide doesn't give you a second chance. It doesn't wake you up gasping. It doesn't trigger panic. It just quietly, invisibly, lethally steals your oxygen while you sleep. Every year, thousands of people die from accidental carbon monoxide poisoning in their homes, in their cars, while camping with portable heaters in enclosed spaces. It's preventable, entirely preventable, but it requires awareness. It requires understanding that suffocation doesn't always look like drowning or choking. Sometimes it's silent, invisible. A molecule you can't see or smell, binding to a protein you didn't know you had,
slowly shutting down your body while you rest peacefully, unaware that you're dying. So carbon monoxide teaches us the same lesson the rest of this journey has been teaching. Oxygen isn't optional. It's not negotiable. Your body has no reserves, no backup plan, no alternative fuel source. You live breath to breath, molecule to molecule, entirely dependent on a continuous supply of oxygen reaching your cells. And when that supply is interrupted, whether by water, altitude, airway obstruction, or a silent gas that hijacks your hemoglobin, the result is always the same: suffocation, cellular failure, death. The only variable is how long it takes. We've spent most of this journey talking about what happens when breathing stops, when oxygen disappears, when the body suffocates. But now, let's flip the script. Let's talk about the systems your body has in place to prevent that from happening. Because suffocation, while always possible, is actually remarkably rare given how fragile the process of breathing is. And the reason it's rare is that your body has built multiple layers of defense, redundancies, backup systems, automatic overrides that kick in the moment something goes wrong. You are, biologically speaking, designed not to suffocate, and the engineering behind that is extraordinary. Let's start with the most fundamental defense: automatic breathing. You don't have to think about breathing. You don't have to remember to inhale. You don't have to consciously contract your diaphragm 12 to 20 times per minute for your entire life. It just happens. And it happens because of a small region at the base of your brain called the medulla oblongata. This is your respiratory control center, a cluster of neurons that fire rhythmically, automatically, sending signals down your spinal cord to the nerves that control your diaphragm and intercostal muscle. The medulla doesn't need input from your conscious mind. It operates entirely on its own, monitoring signals from chemoreceptors and adjusting your breathing rate in real time. Too much carbon dioxide? Breathe faster. Too little oxygen? Breathe deeper. It's a closed-loop system, self-regulating, self-correcting. And it works flawlessly, millions of times over the course of your life, without you ever having to pay attention. This is why you can sleep for 8 hours straight without suffocating. Your medulla keeps working, keeps breathing for you, even when you're completely unconscious. But what if something goes wrong with the medulla? What if it's damaged by a stroke or trauma or disease? Your body has a backup, a secondary respiratory center in a region called the pons, located just above the medulla. The pons helps fine-tune breathing patterns, smoothing out the transitions between inhale and exhale, preventing you from breathing too shallowly or too rapidly. It's not as critical as the medulla, but it's there, a redundancy, a fail-safe. And if both the medulla and pons are damaged, breathing becomes voluntary. You have to consciously remember to inhale, and the moment you lose consciousness, you stop breathing. But that level of damage is rare. Most people never experience it. Now let's talk about the sensors. The chemoreceptors we've mentioned throughout this journey. You have two main types. Peripheral chemoreceptors, located in the carotid bodies near your carotid arteries and in the aortic bodies in your aorta. And central chemoreceptors, located in the medulla itself. These receptors are constantly sampling your blood and cerebrospinal fluid, checking oxygen levels, carbon dioxide levels, and pH. And they're sensitive, incredibly sensitive. A drop in blood oxygen of just a few percentage points is enough to trigger a response. But here's the interesting part. Your body cares more about carbon dioxide than oxygen.
The peripheral chemoreceptors do respond to low oxygen, but the response is relatively weak. The central chemoreceptors, on the other hand, are exquisitely sensitive to carbon dioxide. Even a tiny increase in carbon dioxide levels, a rise of just 2 to 3 millimeters of mercury in partial pressure, triggers a massive increase in ventilation. Your breathing rate doubles, triples. Your body will do almost anything to get rid of excess carbon dioxide. This makes sense from an evolutionary perspective. Under normal circumstances, if carbon dioxide is rising, it means you're not breathing enough. And if you're not breathing enough, oxygen will eventually drop too. So carbon dioxide acts as an early warning signal. A canary in the coal mine. It alerts your body to the problem before oxygen deprivation becomes critical. And in most situations, this system works perfectly. You start breathing faster, carbon dioxide drops, oxygen stays stable, crisis averted. But this system has a vulnerability. If you're in an environment where carbon dioxide is being removed, where you're exhaling it normally but not inhaling any oxygen, your chemoreceptors don't sound the alarm. This is what happens in confined spaces filled with inert gases like nitrogen or helium. You breathe. You exhale carbon dioxide. Your senses say everything is fine, and you lose consciousness without ever realizing you're suffocating. It's a flaw in the design, a blind spot, but it's rare enough that evolution hasn't selected against it. Your body also has mechanical defenses. Your airway is lined with cilia, tiny hair-like structures that beat rhythmically, moving mucus and debris up and out of your lungs. And this is called the mucociliary escalator. It's your first line of defense against inhaling harmful particles. Dust, bacteria, pollen, anything that makes it past your nose gets trapped in mucus and swept back up toward your throat, where you either swallow it or cough it out. You produce about 1 liter of mucus every day. Most of it you never notice because it's constantly being cleared. Then there's the cough reflex. If something irritates your airway, a piece of food, a noxious gas, even just a tickle, receptors in your throat and bronchi trigger a cough. Your diaphragm and intercostal muscles contract forcefully. Your glottis closes, building up pressure in your lungs. Then it suddenly opens, and air explodes out at speeds up to 100 miles per hour. It's violent, effective, and almost entirely involuntary. You can suppress a cough for a little while, but eventually your body overrides your conscious control and forces you to cough anyway. There's also the gag reflex. If something gets too far back in your throat, near your pharynx, your body triggers a gagging response. Your throat contracts. You retch. The goal is to prevent anything from entering your airway that shouldn't be there. It's uncomfortable, unpleasant, but it's protective. And like the cough reflex, it's mostly involuntary. You can't easily override it. Your body won't let you. Even your epiglottis, that small flap of cartilage at the back of your tongue, is a defense mechanism. Every time you swallow, your epiglottis folds down, covering the opening to your trachea. This prevents food and liquid from going down the wrong pipe. It's automatic, coordinated, and it works so reliably that you almost never think about it. But occasionally, it fails. A piece of food slips past, and you choke. Your body immediately triggers a coughing fit to expel the foreign object. Usually, it works. The food is dislodged. You catch your breath, crisis over. But if it doesn't work, if the object is too large or lodged too deeply, you suffocate. This is why choking is one of the leading causes of accidental death. A single mechanical failure,
a piece of steak in the wrong place, and the defenses can't fix it in time. Your lungs themselves have defenses. Alveolar macrophages, specialized immune cells that patrol your alveoli, engulfing and digesting bacteria, viruses, and debris. They're like microscopic janitors, constantly cleaning up, preventing infections from taking hold. Your lungs are exposed to the outside world with every breath. Thousands of microbes enter your respiratory system every day. But most of them never cause problems because your immune system, your cilia, your mucus, and your macrophages stop them. And finally, there's redundancy in the system itself. You have two lungs. If one is damaged, the other can compensate. You can survive with one lung. It's not ideal. Your exercise capacity drops. You get winded more easily. But you can live a relatively normal life. You even have spare alveoli. 300 million of them, remember. You don't need all of them. Smokers destroy millions of alveoli over the course of decades, and many of them still breathe relatively normally because they have so many to spare. The system is over-engineered, built with margins of safety that allow for damage, for disease, for aging. So yes, suffocation is always possible. The systems can fail, the defenses can be overwhelmed. But the fact that suffocation isn't a constant, everyday threat, despite how vulnerable the process of breathing is a testament to the remarkable biological engineering your body has developed over millions of years. You are designed to breathe, designed to extract oxygen from the air and deliver it to your cells. And your body will fight with every tool it has to keep that process going until it can't. So, let's say it happens. Despite all the defenses, despite all the backup systems, despite the body's desperate attempts to keep breathing, oxygen stops, the heart stops, circulation ceases, the person is clinically dead. But here's the thing about death. It's not always permanent. Not immediately. There's a window, a brief period where the damage, while catastrophic, is still reversible, where intervention can bring someone back. This is resuscitation, the biology of bringing the dead back to life. And understanding how it works and why it sometimes fails reveals just how delicate the line between life and death really is. Let's start with CPR, cardiopulmonary resuscitation. It's a technique most people have heard of, fewer have been trained in, and even fewer have had to perform in a real emergency. But the biology behind it is fascinating. When someone's heart stops, when they're not breathing, they're not getting oxygen to their brain. And as we've established, the brain can only survive a few minutes without oxygen before permanent damage sets in. So the goal of CPR is simple. Keep blood flowing. Keep some oxygen getting to the brain. Buy time until professional help arrives. Here's how it works. You place the heel of your hand on the center of the person's chest, right over the sternum. You place your other hand on top. You lock your elbows, and you push, hard, fast. The guidelines say 100 to 120 compressions per minute. That's nearly 2 compressions every second. And you're not pressing gently. You're compressing the chest by at least 2 inches, sometimes more. You might crack ribs. That's normal, expected, because broken ribs heal. Dead brain cells don't. What you're doing, mechanically, is squeezing the heart between the sternum and the spine. Every time you push down, you're forcing blood out of the heart's chambers and into the arteries. Every time you release, the chest recoils and blood flows back into the heart from the veins. You're manually pumping blood, acting as an external heart. and while it's not nearly as efficient as a real heartbeat, while it only generates about 1/4 to 1/3 of normal cardiac output, it's enough, just barely enough, to keep some oxygenated blood flowing to the brain. But here's the problem. The blood you're circulating isn't getting reoxygenated, the person isn't breathing, their lungs aren't exchanging oxygen and carbon dioxide. So the blood that's being pumped to the brain is getting progressively more deoxygenated with every compression, which is why CPR alone isn't enough. You also need rescue breathing. Every 30 compressions, you stop. You tilt the person's head back, lift their chin to open the airway, pinch their nose shut and give 2 breaths, mouth to mouth. You're breathing for them, forcing air into their lungs, hoping that some of that oxygen crosses into their bloodstream and gets carried to their brain during the next round of compressions. It's exhausting. If you've never done CPR on a real person, you don't realize how physically demanding it is. Your arms burn, your back aches, you're sweating, gasping, and you can't stop. Because stopping means the blood stops flowing. And if the blood stops, the clock starts ticking again. Brain damage in 4 to 6 minutes. You keep going until help arrives. Until a defibrillator is available. Until someone else can take over. Or until it's clear that it's not working. Now, let's talk about defibrillation. Because CPR alone rarely restarts a heart. What it does is buy time. Keep the brain alive until you can fix the heart. And fixing the heart, when it's in ventricular fibrillation or pulseless ventricular tachycardia, requires an electric shock. A defibrillator delivers a massive jolt of electricity across the chest, enough to momentarily stop all electrical activity in the heart. The idea is to reset the system, to silence the chaotic, disorganized firing, and give the heart's natural pacemaker, the SA node, a chance to take over again and restore normal rhythm. It doesn't always work. Sometimes the heart is too damaged, too hypoxic, the cells are too far gone. But when it does work, when that shock converts ventricular fibrillation into a normal sinus rhythm, it's one of the most dramatic interventions in all of medicine. One moment, the person is dead, heart stopped, no pulse, no breathing.
The next moment, after the shock, the heart starts beating again. Blood starts flowing,
And if you're lucky, if the downtime wasn't too long, the person wakes up, sometimes minutes later, sometimes hours. But they wake up. They survive. But survival isn't guaranteed, and survival doesn't always mean recovery. Because even if the heart is restarted, even if breathing is restored, the brain may have already been damaged. This is where time becomes everything. Every minute without oxygen increases the likelihood of permanent neurological injury. After 3 to 4 minutes, some brain cells are dead. After 5 to 6 minutes, large areas of the brain may be irreversibly damaged. After 10 minutes, the chances of meaningful recovery drop to nearly zero. There are exceptions. Cold water drowning, as we discussed earlier, can extend the window. Hypothermia slows metabolism. The brain needs less oxygen. Children especially have survived prolonged submersion in icy water and recovered fully. These cases are miraculous, but they're also rare. In most cardiac arrests, in most suffocation events, time is the enemy. And once that critical window closes, no amount of CPR or defibrillation can bring the person back, not the person they were. This is why the concept of therapeutic hypothermia has become standard in post-cardiac arrest care. If someone is successfully resuscitated but remains unconscious, their body temperature is deliberately lowered to around 32 to 34 degrees Celsius. roughly 90 to 93 degrees Fahrenheit. They're cooled with ice packs, cooling blankets, or even cold intravenous fluids, and they're kept at that temperature for 12 to 24 hours. The goal is to reduce the brain's metabolic demand, to slow down the secondary injury that happens after oxygen is restored. Because here's the paradox: restoring oxygen after a period of hypoxia can actually cause additional damage. It's called reperfusion injury. When oxygen-starved cells suddenly get oxygen again, they sometimes produce reactive oxygen species, free radicals, highly reactive molecules that damage cell membranes, proteins, and DNA. It's like a fire that continues to smolder even after the flames are extinguished. Therapeutic hypothermia helps mitigate this. Cooler temperatures mean slower chemical reactions, less inflammation, less free radical damage, and better neurological outcomes. But even with cooling, even with aggressive post-resuscitation care, many people don't fully recover. Some wake up with memory deficits. Some have motor impairments. Some remain in vegetative states, alive but not conscious, because the brain damage that occurred during those critical minutes without oxygen is permanent. The neurons that died won't regenerate. The connections that were lost won't rebuild. The person might survive, but they might not be the same person who went into cardiac arrest. This is the reality of resuscitation. It's not like the movies where someone flatlines, gets shocked once, and immediately sits up, gasping and coherent. Real resuscitation is messy, brutal, and often unsuccessful. The overall survival rate for out-of-hospital cardiac arrest is around 10%. 10%. And of those who survive, many have significant neurological impairment. The odds are not good. But that 10%, those people who do survive, who do recover, they exist because someone knew CPR. Because someone started compressions immediately. Because a defibrillator was available. Because the window hadn't closed yet. And that's the lesson here. Suffocation kills, quickly, permanently, but it doesn't kill instantly. There's a window. A brief, fragile window where intervention can make the difference between death and survival, between brain damage and recovery. The biology is unforgiving. The margins are thin, but they exist. And sometimes, just sometimes, they're enough. So, here we are, the end of our journey through suffocation, through oxygen deprivation, through the biology of what happens when the one thing your body cannot live without suddenly disappears. We've walked through drowning, altitude sickness, carbon monoxide poisoning, cardiac arrest. We've explored the cascade of cellular failure that begins the moment oxygen stops flowing. And we've seen how the body fights desperately until it can't fight anymore. But now, as you lie here, listening, breathing easily, oxygen flowing into your lungs with every effortless inhale, let's talk about what all of this means, what it teaches us, and why understanding suffocation actually helps us appreciate something we take for granted every single day. The breath you're about to take. Take a breath right now, a deep one. Feel your chest expand. Feel the cool air moving through your nostrils, down your trachea, into your lungs. Feel your diaphragm contract, pulling air into the spaces at the bottom of your lungs where gas exchange happens most efficiently. Hold it for just a moment, and then release, slowly. Feel your body relax as carbon dioxide flows out, as your diaphragm relaxes, as your chest settles back to its resting position. That breath, that simple, automatic, unremarkable breath, is the most important thing you'll do today. and you'll do it roughly 20,000 more times before tomorrow arrives. We've spent hours now talking about what happens when breathing stops, but the real miracle isn't death. It's life. It's the fact that your body has been breathing continuously, flawlessly, for every moment of your existence. You took your first breath seconds after you were born. Your lungs, which had been filled with fluid in the womb, suddenly inflated with air. And from that moment on, you've been breathing as a baby, as a child, as a teenager, as an adult, through sleep, through illness, through stress and joy and fear. Your body never forgot, never stopped, never needed a reminder. Think about that. Your heart has beaten roughly 3 billion times in your life. Your lungs have inflated and deflated hundreds of millions of times. And almost all of that happened without your conscious involvement. Your medulla oblongata, that small cluster of neurons at the base of your brain, has been sending signals to your diaphragm every few seconds for decades. It will continue doing so until the day you die. It's the most reliable system in your body, more reliable than your digestive system, more reliable than your immune system, more reliable than almost anything else, because it has to be. Because if it stops, even for a few minutes, you're gone. This is why breathing is so tied to mindfulness, to meditation, to relaxation, because breath is the bridge between your conscious and unconscious mind. It's the one automatic process you can also control voluntarily. You can slow your breathing, deepen it, hold it, change its rhythm. And when you do, you send signals to your nervous system. Slow, deep breaths activate your parasympathetic nervous system, the rest and digest system. They lower your heart rate, reduce your blood pressure, tell your body that it's safe, that there's no emergency, that you can relax. This is why breathing techniques are so effective for anxiety, for panic attacks, for insomnia. Because when you're anxious, your breathing becomes shallow and rapid. You're hyperventilating slightly, blowing off too much carbon dioxide, shifting your blood pH, and that shallow breathing sends signals to your brain that something is wrong, that you're in danger. It creates a feedback loop. Anxiety causes rapid breathing. Rapid breathing reinforces anxiety. But you can break that loop by deliberately slowing your breath, by breathing in for 4 counts, holding for 4, breathing out for 4, holding for 4, box breathing, it's called. And it works, not because it's magic, but because it's biology. When you slow your breathing, you increase carbon dioxide levels slightly, just slightly, enough to shift your blood pH back toward normal, enough to tell your chemoreceptors that everything is fine, and your chemoreceptors, in turn, tell your brain that there's no emergency. The autonomic nervous system shifts from fight or flight to rest and digest. Your heart rate slows, your muscles relax, and the anxiety fades, not completely, not instantly, but gradually. Because you've taken control of the one physiological process that links your mind to your body, your breath. This is also why sleep apnea is so damaging. Sleep apnea is a condition where your airway repeatedly collapses during sleep, cutting off airflow for 10, 20, 30 seconds at a time. You're suffocating, briefly, repeatedly, all night long. Your oxygen saturation drops. Your brain detects the hypoxia and partially wakes you up, just enough to restore muscle tone, open the airway, and let you breathe again. Then you fall back asleep. And it happens again, dozens of times, sometimes hundreds of times per night. You're cycling through mini suffocation events, over and over, without ever fully waking up. and the effects are devastating. Chronic sleep deprivation, high blood pressure, increased risk of heart attack and stroke, cognitive impairment, depression, weight gain, all because your body isn't getting enough oxygen during sleep. All because breathing, that automatic, reliable process, is being interrupted. This is why CPAP machines, which deliver pressurized air to keep your airway open, are so effective. They don't cure sleep apnea, but they prevent the airway collapse. They ensure continuous breathing, continuous oxygen delivery, and people who use them report life-changing improvements. Better sleep, more energy, clearer thinking, because their brain is finally getting the oxygen it needs. All night, every night. So what's the takeaway from all of this? From this long, dark exploration of suffocation and oxygen deprivation? It's simple. Breathing matters. Oxygen matters. More than almost anything else. You can survive weeks without food, days without water, but only minutes without oxygen. Your entire existence, your consciousness, your ability to think and feel and experience the world depends on a continuous supply of oxygen reaching your brain, and that supply depends on breathing, on healthy lungs, on clear airways, on a functioning cardiovascular system, on hemoglobin that isn't hijacked by carbon monoxide, on altitude that isn't too high, on water that stays outside your lungs. We don't think about breathing because we don't have to. It's automatic, effortless, background noise in the symphony of being alive. But maybe, after this journey, you'll think about it a little more. Maybe you'll appreciate the next breath you take. The quiet miracle of air moving into your lungs, oxygen crossing into your blood, energy being produced in your mitochondria, and consciousness continuing uninterrupted because of that one simple, automatic, life-sustaining process, breathing. The thing you do 20,000 times a day. The thing you'll do millions of times in your life. The thing that, more than anything else, keeps you alive. So, as you drift off to sleep tonight, as your breathing slows and deepens, as your body shifts into rest mode and your conscious mind fades, know that your medulla oblongata is still working, still sending signals, still keeping you breathing, even when you're not aware of it. Even when you're dreaming, even in the deepest stages of sleep, your body is protecting you, keeping oxygen flowing, keeping you alive, breath by breath, moment by moment, until morning comes and you wake once again to take that first conscious breath of a new day. And maybe, just maybe, you'll appreciate it a little more than you did yesterday, because now you know. Now you understand what it means to breathe and what it means to stop.